So since we're in the reactions unit, we are going to be looking at reactions at a little bit of a zoomed in scale. And one of the things that we're going to do is we're going to look really closely at these two types of reactions that we call a single replacement reaction and a double replacement reaction. And in order for us to understand what is going on and the chemistry sides of these reactions, we have to have an understanding of something that we call dissociation. Okay? So dissociation is a really fancy chemistry term for splitting up or dissolving in water. And so you can probably think of a really common example of this being when you take a little bit of NaCl, which is just table salt, and you stir it into some water, right? What you see at the eye level is you see that the salt, quote unquote, disappears into the water solution. When that happens, right, what is happening at the chemistry level is a lot more complex than what you see at the eye level. Okay, so what's really happening here is if I take some sodium chloride, and this comes in a form of crystals, sodium chloride is an ionic substance. And when ionic substances are added to water, they dissolve because the water molecules, which is as we know from the IMF's unit, a polar substance, what they do is they peel those ions, the cations, the sodiums, and the anions, the chlorines, away from each other, and they dissolve them or separate them into ions in the solution, okay? What we call this is, we call this an aqueous solution. So when I add an ionic substance into water, what that becomes is what we call an aqueous solution. So when you hear the word aqueous, you might hear the word aqua or agua if you speak Spanish, okay? This is just a water-based solution with ions dissolved into it. So the ions dissolve into the water. Okay, and that because water is polar, it can peel apart and separate ionic substances into their individual ions. Okay, another way to visualize this is there's a little bit of a simpler picture here. This is my net ionic visual aid here. Now, if I were to take one formula unit or one compound of NaCl, okay, you can think of it being made up as a 1+ ion and 1- ion, being the chlorine. It would separate into its two ions here. Okay, so into 1 sodium plus and 1 chlorine minus. The way we write that is we write that with something that we call an ionic equation. The ionic equation shows you how many of each ion type are in the solution. Okay, and so in this case, we have 1 Na plus and 1 Cl minus. Okay, and so as we're doing that, right, as we see that, how we write it is we say that there's 1 sodium plus, we put the charge in the top right-hand corner, and then at the bottom of it as a subscript, we write aqueous. Okay, and we have 1 chlorine minus. What would happen, though, is if we had 4 NaCls to start. What would happen? Okay, well, instead of separating into 1 sodium and 1 chlorine this time, we're going to have a total of 8 ions. 4 of them are going to be our sodiums, and 4 of them are going to be our chlorines, or our chlorides. Okay, and so the way we write this is now to indicate how many unique ions there are of each type. We're going to use a coefficient and put that in front of each element symbol. So you have 1, 2, 3, 4 sodiums here, and 1, 2, 3, 4 chlorines there. Okay, both of them are aqueous because aqueous means you're separated in ions, and these are separate ions dissolved into solution. Okay, so a little bit more of a complex example. What happens when we have subscripts next to the element symbol? So for instance, we have ZnBr2. That little 2, this little subscript, tells us that there's 2 Brs in 1 ZnBr2 compound. Okay, so since these are just individual elements here, what's going to happen is that those zincs, the zinc, which is 2+ in charge, is going to separate from the 2-1 bromine ions. So the way we're going to write that is 1 Zn plus 2, aqueous, because it's an ion, plus 2 Br minus, because we have 2 of these ions here. All right. Now, let's say that we have a coefficient and then we have a subscript. What's going to happen is if we have 3 ZnBr2s, we have 3 of these compounds here. Okay. And we can see, for instance, that we have 3 zincs because there's a 3 out in front of here and there's a hidden subscript of 1 here. And we're going to have 6 bromines because there's a subscript of 2 next to bromine and a coefficient of 3. So whenever you have a coefficient, right, you multiply that by whatever subscript's present in the chemical formula. So now we're going to have 6 total bromines here. So when they dissolve into solution, we would write 3Zn2 plus and 6Br minus. Okay? All right, the last example that we have is when we have a polyatomic. Okay, so a polyatomic ion that comes from the back of your periodic table ion sheets that you would use in class, something like a sulfate, right, stays together as one unit when it dissolves in solution. So these polyatomic ions, basically the sulfur and the oxygens are very stable when they're connected together, so they're not going to split up into individual sulfur and oxygens in water. What's going to happen instead is the 2 sodiums that we have in this sodium sulfate are going to separate into their individual ions, and then we're going to peel off that one polyatomic group, and that's going to be a group on its own. So the way that we're going to write this is 2 coefficient of 2 Na plus 1 SO42 minus. Okay, now what happens when you have multiple of the element in one of the polys? You do the same thing. We're going to have 4 sodiums, so we're going to take 2 times the subscript a little 2 here. So we're going to have 4 sodiums. And then we're going to do 2 times the sulfate. So kind of like when we're balancing equations, the coefficient applies to everything to the right of it. So that would be written as 2 SO42 minuses, all right, or minus 2s. Notice how I'm not multiplying the charge here. I'm keeping the charge the same. You're writing the charge in the top right-hand corner of one individual sulfate always, or one individual sodium. The charges of each of these individual ions do not change with the number of the ions. Okay? And then the last example is what happens when this gets a little bit more complex. Okay? When it gets a little bit more complex and we have a subscript outside of parentheses with this polyatomic of nitrate, what do? Well, kind of like we did before, we're going to pull the subscript to the front and we're going to multiply that by the ion. Okay? So that will tell us how many are each. So we're going to have 1 calcium, okay, because we just have a 1 there. There's no subscript. And we're going to have 2 nitrates. So we pull that subscript of 2 to the front, and we have 1, 2 nitrates. So the way we're going to write this is 1 calcium 2 plus 2 NO3 minus. Again, keep the charge of each of these -1. That doesn't change, ever. You look that up on the back of your periodic table. Now, let's say I have a coefficient and a subscript around a polyatomic. Those 2 numbers get multiplied together, okay? So we're going to have 3 CAs, because there's a 3 in front of a hidden subscript of 1 for Ca. And then we're going to do 3 times 2, that little subscript around after the nitrate, and we're going to bring that out in front of the nitrates formula. So we're not going to change the formula of the poly. We're just going to indicate how many there are once it's dissolved into solution. In this case, it will be 6. So pretty much, take your subscripts and bring them to the front when you're writing out these ionic equations. And then if there's a coefficient, make sure to multiply that subscript by that coefficient number. So let's take a few examples of how we would do this in a molecular form and how do we convert that to the ionic form, okay? So one thing I want to show you real quick is before we get started, these 2s and these coefficients and subscripts matter because it totally changes the way that you build the compound or build the molecule. So when I look at Cl2, what Cl2 is this is a chlorine attached to another chlorine. All right, so this here is an element or a molecule. It is not charged, so this is not an ion. If I wanted to write the ion form of chlorine and make it a chloride anion, what I'm going to do is I'm going to use the big 2. So the little 2 in this case tells us that there's 1, 2 of these chlorines attached to each other. Big 2 means that you have 2 chlorines, but they're not attached to each other, okay? And they have charges. So 2Cl minus, right? If you leave this in this form when you're writing out these ionic equations, you are not going to be writing out the proper format here. Okay, so you have to use big coefficients and pull those subscripts to the front when we're writing out ions to show that they're separate. Okay, so little 2 means they're attached, like the big 2 coefficient means they're detached. So let's go ahead and work through a few of these. All right, so zinc chloride, ZnCl2. So as I said earlier, we're going to take the little 2 and pull it to the front for the chlorine. In this case, we only have 1 zinc. So we're going to go zinc, we're going to add a charge, and since it came from something that's aqueous, we're going to assume that it's also going to be aqueous as an ion and dissolve. So that's an AQ there. Now the 2, where the chlorine was, that's going to be pulled to the front of the chlorine. So now we're going to have 2 Cl minus, and that will be aqueous. Okay, now let's go to the next one. It says here to make sure that you do not separate polyatomic ions. That's really, really important here. So let's look at this. This OH and this OH2, see that's in parentheses? That means that's a polyatomic, okay? So when we separate this out, we have 1 K. Each K has a +1 charge. And again, you can write +1 or you can do 1 plus. It doesn't matter the order of the sign and the number, or you can just simply put a plus. It all means the same. And we're going to add this to 1 hydroxide. So a lot of students here would be tempted to split it up into O and H, but since it's a polyatomic, it's going to stay together. So this is going to be +1 OH minus, because that's the charge you find in the periodic table, and that will be aqueous. Why don't you go ahead and try magnesium hydroxide, this next one right here. All right, let's see how you did. So we have 1 magnesium. This 2 does not apply to the magnesium, since subscripts only apply to what's immediately to the left of it. We're going to have Mg, we're going to have 2 plus, and this is going to be aqueous. All right, now we're going to pull the subscript to the front of this hydroxide group, and this time we're going to have 2 hydroxides, them being aqueous. Okay, so here are a few more examples where they get tricky, and we're going to have some polyatomics involved again. Okay, so as you can see from my example, you can see that I'm multiplying the subscript by the coefficient to get 4Li here, and then you're applying this coefficient to this one all the way to the right. So there's 2 O2 minuses. Okay, and by the way, you know the charge of an oxygen and a lithium because of the families on the periodic table. So lithium being an alkali metal, we should know by now that's a +1 charge. The oxygen family elements have a -2 charge. Okay, so let's go ahead and do the next one. We have a 2 and then a subscript a little 2. That means we have 4 aluminums. The aluminum family or the boron family on the periodic table is the 3rd column, so that's a 3+ charge, and that's going to be aqueous. Now we're going to take this 2 and we're going to multiply it by that 3 after the sulfate. So now we have 6 sulfates. Never change the formula of a poly, just like in formula writing. Each of those are 2 minus if you look it up on the table, and we're including our state of matter being aqueous because it came from something aqueous. All right, why don't you try the next one? Here's the next one. We got a 4 times a 2. This could be 8 Na, and each sodium being an alkali metal is plus, so hopefully you look that up on your periodic table. This is aqueous. Plus 4 times the sulfur, there's only 1 because there's no subscript, and each sulfur being in the oxygen family has a 2 minus charge, also going to be aqueous. All right, the last one, let's do the last one together. So this one's really weird because we have a polyatomic in the first position. This is the cation of ammonium. This is one of our only polyatomic cations we're going to use. Ammonium is going to basically act like a metal in this case. So what we're going to do is we're going to treat it as if it's the positive ion here. So we got 2 ammonium, 2 in front of the ammoniums, and we have a subscript of 2 after the parentheses, which means that we have 4 NH4 pluses, and that's going to be aqueous. And that 2 is going to apply to the carbonate at the end. There's only 1 carbonate, so be careful. A lot of students would be really tempted to put CO6 here, but you should never change the formula of a polyatomic. So keep it as 3 and just put the 2 out in front. Then the charge of each carbonate on the periodic table, if you look up the ion sheet, is 2 minus, and that's going to be aqueous. So this is a skill that's really important to not get lost in the details. The details being you have to include states of matter next to everything that's aqueous and a charge next to everything that's aqueous. Now, what do we do if an equation has some things that are aqueous and some things that are solids? So in this case, this is what's called a double replacement reaction. We'll look at them a little bit more closely later in the chapter. There are 3 aqueous compounds here, and there is 1 solid compound here, that lead iodide. If you remember, lead iodide was actually what we demoed in class. This is what we call a solid precipitate. So this here, when you add or create lead iodide in a test tube, this is going to be insoluble, okay? Meaning it will never dissolve in water. So when I have something with an S next to it, that means solid, okay? You are never going to split that. So this, you do not split into ions. Because no matter how hard you try, something like lead iodide, a precipitate, will never split into ions, okay? However, when you see something AQ, AQ means that you are going to split these into ions. So all three of these, you split into ions. Okay, so let's look at the big idea of this here. Well, what can we do with this dissociation skill? So now we can look at equations for single replacement reactions more in detail and write two new further extended equations from a balanced chemical equation, okay? So these are called complete and net ionic equations. So the tips and tricks and how to complete this, it's kind of a four-step process. The first thing that we're going to do is we're going to determine the products of the reaction we're looking at. Then we're going to balance your equation with coefficients. So let's do the first two steps on this example problem below, okay? So whenever I give you a problem, what we're going to start doing in class is we're going to start predicting products of reactions, so filling in the product blanks, and balancing equations like we did last chapter. So when I look at this, I see there's a zinc and there's a hydrochloric acid. Zinc is a solid and HCl is aqueous. We have to think about what reaction pattern this matches. Okay, so I'm going to give you a second to think about that. So what I see here is I have an element and I have a compound. Or you can think of it as A plus BC turns to what? Okay, so if our pattern is A plus BC, or an element plus a compound, it's probably going to be a single replacement reaction, where this solid zinc, if it's more reactive than hydrogen, is going to come on in and replace it in the compound, therefore kicking H out. All right, so when we write the products of this reaction, what we're going to do is we're going to place the zinc with the chlorine. However, a lot of students are going to stop here and they're going to say, well, that's a balanced chemical equation and I want to keep the number of zincs and HCl's the same on each side. But if you recall, if you look on your ion sheet, zinc is 2 plus, Cl is 1 minus, so that means this is ZnCl2. Again, don't worry if the chlorines don't match. That doesn't matter because we can go back with coefficients and balance the equation for numbers of atoms after. All right, now we're going to add the other product. The other product is if we kick the H out, now the H is on its own, but remember, Hofbrinkel, the creepy clown, this is a diatomic element, so it always comes in pairs of 2. Don't worry, I know there's only one H over here right now, but we can fix that in post, okay? Now, what do we do next? Well, next, it says to determine the states of matter of each of these reactants. How do I do that? Well, if elements are involved, you can find the states of matter using the periodic table in the classroom. Okay, so the periodic table in my classroom has some different colors for some different elements. Since we're not in the classroom right now, we can just think about what we think the element's state of matter is, just based on some common sense looking at our equation. Okay, so for our elements, we have hydrogen. Okay, we've looked at hydrogen a lot in our class. Hydrogen, you probably know, is a gas, so you're going to just put a little G next to the hydrogen there. Now, it says for compounds, we can assume that they are all soluble or aqueous. Okay, so compounds are always going to be aqueous for right now. Later in the chapter, we'll adjust that a little bit, but for right now, we're going to assume any compound we make is aqueous. So the zinc chloride is going to be aqueous. All right, so those are our states of matter. Now we're going to go ahead and balance our equation. So here, we're going to add a 2 in front of the HCl. And by doing that, now I have 2 H's on this side and 2 chlorines. Okay, so we're all balanced and ready to go. Okay, so let me clean this up a little bit so we can see our chemicals a little bit more clearly. What we're going to do now is we're going to write what's called the complete ionic equation. And this is where we're going to be breaking things apart into their individual ions. Okay, so we're going to break up aqueous compounds here into their ions. But we're going to leave non-aqueous solid liquids and gases alone. Okay, and we know their states of matter based on what's in the parentheses next to the element. So that means we're going to leave solids with S's, liquids with L's, and G's alone when we do this process. Okay, so here's the complete ionic. When I look at my equation, once it's balanced and once I've written proper formulas, now I'm going to be adjusting and writing the full thing out. Since my first chemical is zinc solid, I leave solids alone, so I copy it down exactly as I see it. Now, I got 2 HCl. HCl is aqueous. What that means is we have to split this into its ions. So just like we did on the first page, we're going to do 2 times H, and we're going to write down the charge of each hydrogen Since it's in the alkali metal family, it's going to be a plus charge, and we're going to write down that it's aqueous. So for any ion, you have to write the state of matter in parentheses and the charge. Now we're going to have 2 times the Cl portion. So chlorines have a -1 charge, and they are also aqueous. And there's 2 of them because that coefficient of 2 also applies to the chlorine. So anything that comes from an aqueous compound will also be aqueous. Okay, so that's how I know to write those ions as aqueous. Now the zinc chloride, is this an aqueous compound? Yes, it is. So that means that we have to write out this in ion form. So each zinc has a 2+ charge, if you look at the back of the periodic table, and that's also aqueous. And we're going to pull this 2 in front of the Cl, and we're going to write this as 2Cl minus, and that's going to be aqueous. The last thing that we have is we have hydrogen gas. Up here, if I check, it says to leave solids, liquids, and gases alone. So that means that we're just going to keep the hydrogen gas as is. Okay, so the complete ionic equation is when you're talking about the reaction. This is every single thing that happens and every single thing involved, right? Every ion, everything there. But as you know, like when you're talking about something that you did over the weekend, or let's say you go to a sports game, right? You don't talk about every single person that attended the sports game. You usually just talk about the players involved on the court, okay? And so the net ionic equation is a summary of the reaction, but it only includes the key players. So what we have in the complete ionic equation is something called a spectator ion. Spectator ions are ions that don't participate in the reaction because they look exactly the same at the beginning and the reactant side, and exactly the same at the end in the product side. So just like when you go to a sports game and you're a spectator, when you talk about the game, you usually don't talk about the spectator fans, you talk about the players on the court doing the things. In chemistry, our spectator ions don't partake in the reaction because they're not used up during, so they're the same before and after as reactants and products. So when I look at my complete ionic equation, can you guys spot who the spectator is or who is the exact same on either side of the arrow? Well, hopefully you're able to spot that the 2Cl minus is exactly the same. You have to have the exact same charge and state of matter to be considered the same. So what we do with our spectators is we go ahead and we cancel these out. Okay, so when we cancel these out, basically we eliminate them in the net ionic equation. So what we do is we just copy down the only things that were involved in the reaction that are different on either side of the arrow, and we write down everything there except for the spectators in the net. So this will be the first 2 items, which are not the same as the second 2 items on the right of the arrow. Okay, so what this is really saying is this is saying, when I have this finished, that we are basically summarizing the reaction. We took solid zinc, and that zinc turned aqueous as it dissolved. As the zinc is dissolving, we're taking dissolved hydrogen ions in the acid, the hydrochloric acid, and converting them into the gas form. So when I did this in class and I added some zinc to some HCl, you saw the production of a bubble, which was this hydrogen gas. And we saw that the zinc somewhat disappeared, or quote unquote disappeared, into the solution, which was really it turning from the solid to the aqueous form. Okay, so this net ionic equation tells us the key players involved in the reactions, and we're not involved and not worried about the chlorines because those didn't partake in the reaction at all. So that is your net ionic equation, which are basically just extended versions of a single replacement reaction and talking about a few more details. So, chemistry, go on down here and try out the chemistry section. Good luck. And one more thing I wanted to mention is as I was going through the chemistry section, I added this to your chemistry problems. You guys were going to try 3 or so for me before you came into class the next day. I have summarized a little bit of the key points to keep track of for each of these types of equations as you're writing things. So this is something that's helpful at the end of your chemistry section that you can take a look at. So for your complete ionic equation, you're going to use this if the balanced chemical equation could be written. So we're going to talk about this a little bit more in our lab. Break down only aqueous compounds into their ions, no charges written for solids, liquids, or gases, and keep polyatomic ions together if they're in the equation. Cancel out ions for the net ionic equation that are on the both sides of the arrow. No charge at all should be written for solids, liquids, or gases. And again, keep your polys together. Okay. So when you look at what our example here, we didn't have any polyatomics, but notice my solids, right, and my gases don't have any charges after them. Okay? Sounds good. All right.